All right. So first, I want to thank organizers for inviting me to give this talk. It's really nice that I can share some new results of loop quantum gravity to the asymptotic safety community. In this talk, I'm going to introduce some recent results about UV fixed point of loop quantum gravity. And this talk is based on some recent papers listed here. Before talking about UV fixed point of loop quantum gravity, I want to review briefly the UV fixed point of QCD. And we know that QCD is asymptotic free because it has the UV fixed point that is a free theory of gluons and quarks. And due to this asymptotic freedom, QCD can stand alone as a fundamental theory of nature rather than a low energy effective theory because it's well defined at high energy. And here are some quotes by the people who discover the asymptotic freedom. And here they mention that QCD provides a perfect complete theory and it's better than it has to be. And to be complete, when going from UV to IR, QCD becomes strongly coupled and the perturbation theory fails. And then people use lattice theory to study QCD at low energy. All right, so these are QCDs. Now let's look at the UV fixed point of loop quantum gravity. And the result is loop quantum gravity is asymptotically topological. So very recently, a candidate UV fixed point is identified operationally for covariant loop quantum gravity. This fixed point theory is topological, so it is scale invariant, scale independent, and it is triangulation independent. And that's why we call it fixed point. The theory has no bulk degree of freedom, and physical degrees of freedom only live on boundary. And similar to QCD, because of this UV fixed point, loop quantum gravity is likely UV complete, and it can stand alone as a fundamental theory of nature. And this UV fixed point, this UV fixed point theory also defines the continuum limit of spinfoams because it is triangulation independent. Moreover, loop quantum gravity is well behaved at both UV and IR, and in this sense, the situation of loop quantum gravity is actually better than in QCD. Indeed, when we go beyond the UV regime, loop quantum gravity becomes strongly coupled. So we use spinfoam on lattice, like in QCD. We have to use lattice theory to study spinfoams and loop quantum gravity. And then when we go to the infrared regime, we can actually develop a different weakly coupled perturbation theory. And we find the IR fixed point, which is a free theory of spin to graviton. All right, before we come to details, let me explain what are UV and IR in the previous picture. So in standard quantum field theory, the renormalization group energy scale or length scale is external because the background metric is external. And the energy scale or length scale depends on the background metric. However, for background independent quantum gravity, there's no fixed metric. Therefore, there's no external scale. The scale has to come from the dynamical quantum geometry. It has to come from the theory itself. Consequently, the scale itself has to be a dynamical variable in quantum gravity. So this is actually an important feature of spinfoam, that the spin J in spinfoam plays a dual role. On one hand, it is a dynamical variable. On the other hand, it is a scale because it gives the quantum area and relates to the spacing of the lattice. So in our proposal, we would like to use the expectation value of spin as a scale. This is the analog of the renormalization group scale. And here for small J expectation value, the area is at the same order as the Planck scale. So this corresponds to the UV regime. And for large J expectation value, the area is much larger than the Planck scale. So this is the infrared regime. All right, the UV fixed point that we mentioned previously is in the small j regime. That's why it's called UV fixed point. And here are some features of this fixed point. So first, there's a finite dimensional vector space spanned by some states called boundary blocks, which only depend on boundary degree of freedom. And each boundary block is a linear functional over the space of spin networks. And the complete spinfoam amplitude is a finite linear combination of these boundary blocks. This resembles typical features of topological quantum field theory. So when we turn on perturbations to deform the theory away from this fixed point, so they introduce defects, they introduce defects to the topological theory and make the bulk degree of freedom propagating. So then the amplitude actually reduced to the summing over the summing usual spinfoam amplitude over lattices.
Okay, so there's a raised hand by Alexei.
Okay.
Hello. Sorry for interrupting you. I'm not really familiar with loop quantum gravity, so my question might be dumb. But the thing you stated that LQG is asymptotically topological. Is it in any way dependent on dimension? I mean, is it for 4 dimensions only, or is it true in an arbitrary amount of dimensions?
So this is for 4 dimensions. So
okay.
in the entire the talk is the working dimension is 3 plus 1.
Oh, okay. Thank you. Sorry.
Okay, is there any other question? Okay, so let's continue. So these slides is basically some outline of the key result. And so in the rest of the talk, I'm going to provide some details. So this is the outline of the rest of the talk. So first, I will introduce the notion of spinfoam stack. And it's a sum of spinfoams over a family of 2 complexes. And these are some key objects that is used for this investigation. And then I will define the so-called stack amplitude and the complete amplitude. And the complete amplitude sums over all complexes. So by the way, so here complexes means triangulation. So I will explain a little bit more later. So then I will explain the mechanism of condensation of quantum geometry. That is in the stack amplitude, spins concentrate at specific small values. And then we can develop a UV perturbation theory due to this condensation. And then the UV fixed point is the weak coupling limit of this perturbation theory. At this limit, the stack amplitude and the complete amplitude reduce to a finite sum of boundary blocks, like showed last slide. Finally, if I have enough time, I will briefly discuss the infrared fixed point. All right, so now let's first give a brief introduction of spinfoam theory. Spinfoam theory provides the covariant path integral formulation of loop quantum gravity. And this describes the 4-dimensional dynamics of quantum spacetime. So on the left, for a classical spacetime, the gravity dynamics is described by 4 metric mu nu and describe a time evolution of 3D geometry. So here from the evolution is from some 3D metric HAB in on the initial slice to the final 3D metric HAB out on the final slide. Well, on the right is the loop quantum gravity picture, and the corresponding picture is that the quantum in loop quantum gravity, the quantum 3D geometry is quantized to spin network states, and the initial and final quantum 3D geometries are initial and final spin network states. Okay, so what are spin network states? A spin network state consists of the following data. So first, it has the graph. So this graph has links and the nodes. And then on this graph, we have a spin coloring each link, SU2 spin coloring each link, and a SU2 intertwiner or invariant tensor coloring each node. Okay, so all this data, the graph and the spins and intertwiners are basically the spin network state. And all this data, namely all these spin network states, span the loop quantum gravity Hilbert space for quantum geometry of the spatial slides. Okay, and then the time evolution of spin network nodes, okay, create edges in 4 dimensions, and the time evolution of spin network links create phases. So create phases in 4 dimensions. And the lattice created in this way is called a 2 complex. Okay, so a 2 complex contains a 2 complex contains a number of phases and a number of edges that are on the boundary of the phases, and a number of vertices that are on the boundary of the edges. Okay, so this is roughly speaking the definition of the 2 complex. Then the loop quantum gravity quantization of 4-dimensional geometry is a time evolution history of spin network. The history of spin network is called a spinfoam. And generally, a spinfoam is defined on a 2 complex. It's basically this kind of 2 complex and colored by spins and twiners. And therefore, the summing over histories of spin networks corresponds to the sum over quantum 4-dimensional geometries. And it defines the spinfoam amplitude, and which is the loop quantum gravity formulation of gravitational path interval. Okay. Now let's introduce the concept called spin network, called spinfoam stacks. A spinfoam stacks represent a covariant history of spin networks that has multiple links between a pair of nodes. So namely, this kind of spin network graphs, you have several links between a pair of nodes, and the time evolution of this link these links create multiple phases. So these are called stacked phases. And the spinfoam on this kind of complex is called spin. It's actually a sum over these complexes. It's called a spinfoam stack. Okay. So here, as I said, the spinfoam links evolve into spinfoam phases, and nodes evolve into edges. So therefore, though you have multiple links shared by a pair of nodes, evolve to a stack of phases sharing boundary edges. Okay, and so here, this diagram on the right means that you have a stack of internal phases. So for an internal stack, and the entire boundary cycle is shared by all stack phases. So on the diagram on the left is like a boundary stack of phases, and you have boundary spin network. So these phases, these complexes evolved from the spin network downstairs, and you have all those phases sharing the same boundary edges. It's just because the links are shared same pair of nodes. Okay, so now a stacked 2 complex is created by stacking phases on the root 2 complex. So here, the definition, a root complex is a 2 complex where the phase multiplicity is always 1 for each boundary cycle. For example, this diagram is a root complex, and these diagrams are stacked complexes. So a stack 2 complex is generated by increasing phase multiplicities arbitrarily. And these stacked phases share the same set of boundary edges. So this is the key point. Okay, so given a root complex and the family of complexes generated by stacking phases, the stack amplitude is just the sum of spinfoam amplitudes over all complexes in this family, and weighted by complex parameter lambda f. Okay, so this is this coupling constant or complex parameter lambda f. So each term, this sum is just a standard EPRL KKL spinfoam amplitudes. So these are some standard spinfoam amplitude studied in loop quantum gravity community. And so here I review briefly the construction of this EPRL KKL amplitude. So for each internal phase of the complex, so it's associated with a principal series irreducible representation of SL2C satisfying the simplicity constraint. So this is the simplicity constraint. And the single phase partition function here is denoted by tau. And it depends on K, which is 2 times half integer spin. And it also depends on some SL2C holonomies. So these SL2C holonomies are along each half edge on the boundary of the phase. So these are the SL2C holonomies, and this is shown in the diagram on the right. So each half edge of the phase is associated with SL2C group element GVE or GVE prime. Okay, so these are SL2C holonomies, and these are the variables entering the single phase partition function. And since stack phases, they all share the same boundary edges, and their partition functions share the same set of SL2C holonomies. And the boundary phase partition function is very much similar. So, well, the difference is that in addition to the spins and SL2C holonomies, it also depends on SU2 holonomies on the boundary links, and because there are boundary spin network states, and those states are functions of those SU2 holonomies. So, and these boundary partition function, boundary phase partition function depend on also these SU2 holonomies. And so now the EPRL KKL spinfoam amplitude is just given by making product of all those phase partition functions over all phases. And so basically each phase you have these phase partition functions depending on whether internal phase or boundary phase, and you just product all those phase partition functions, and followed by integrating over all SL2C holonomies, integrating over all these SL2C holonomies, and summing over all the spins. Yeah, so that's basically all the variables depend that those partition functions depend on. Okay, so for each stack of phase, we sum over unordered tuples of non-zero spins, and all those spins are non-zero. So we also introduce a spin cutoff, and so it's introduced in this way. That let EK to be a sequence of positive integers monotonically increasing polynomially. For example, this EK can be just K times K plus 2, and also other choice work equally. So we define the cutoff function alpha to be just a sum of EK over all these stack phases. And we impose that this alpha is bounded by some finite cutoff A. And this cutoff A guarantees that all these sums in this formula become finite. The sum over multiplicity and sum over spin are all finite, are all truncated. Yeah, so this guarantees amplitudes to be finite. Okay, and the stack amplitude can be written in a more compact formula instead of the formula in terms of sum over complexes. And so the previous formula as a definition, it involved basically a summing over complexes in the family. But now we can use a more compact formula using a single integral. And here, in the integrand, each of these omegas is a partition function of a stack of phases instead of a single phase. And for each stack of phase, the partition function omega is the state sum over firstly the multiplicity P, and then the spins from K1 to Kp. The summand is just a product of single phase partition function tau over all phases in the stack. And here, this theta function is a step function imposing the cutoff. Okay, so this is the partition function for an internal stack of phases. And for each boundary stack of phases, the structure is very similar. It's the only difference is that it's the partition single phase partition function depend on boundary SU2 holonomy. Okay, so we have those state sums. The complete amplitude is then obtained by further summing these stack amplitudes over root complex, because each amplitude is defined with respect to root complex, and only summing over the stack complex is generated from the root complex.
So, sorry, Muxin, there was a raised hand by Zois.
There was
a raised hand by Zois.
Okay.
Zois, do you want to ask a question?
Thank you. So how the question is about the cutoff. How can I understand this in a more, let's say, intuitive terms? Like, is this an energy cutoff? Can I view this like this?
Okay. So intuitively, so usually the spinfoam has divergence. So the summing over spin is unbounded. So suppose you work on classical SU2 group, and the summing over spin is unbounded, and then there's a bubble divergence. And in particular, if you stack faces, actually create bubble divergence because you have closed surfaces. So usually it's, you will get divergence, and then you definitely need some cutoff to regularize this state sum to have a finite, well-defined result. And it's so this is actually interesting perspective of this work. Well, probably conceptually for spinfoam in general, is that this cutoff actually plays a role, part of the coupling constant that I mentioned earlier. So which results in the UV perturbation theory. So this cutoff is related to the coupling constant you will see in a moment. And furthermore, and in the spinfoam picture, usually this cutoff of spin intuitively relates to cosmological constant. So this is, I don't know if it answered your question or not, but this is like
I think it did. Thank you.
Story. Okay. All right, let's continue. I think, so we have done that. All right, so now let's look at the complete amplitude. So the complete amplitude is obtained by summing those stack amplitudes over root complexes. And there are infinite number of arbitrary coefficients in this sum, because there are infinite number of root complexes that you can make. In addition to, okay, so firstly, you have summing over complexes within this family of stacking. So there was coefficients in that sum. And furthermore, there are also additional infinite many arbitrary coefficients in this sum. And those ambiguities, all these coefficients are ambiguities. So these ambiguities are equivalent to the triangulation dependence of spinfoam amplitude. Okay, so this is also analog of infinite ambiguities in non-renormalizable quantum field theory. Okay, so now we in this study we restrict the root complex in the sum to satisfy the following conditions. So firstly, we only consider simply connected complex. So all of them are simply connected, because if we look at local quantum gravity process, the involved space-time region is always simply connected. Okay. And secondly, they all have identical boundaries. So namely, we consider the amplitude with fixed boundary state. Okay, so in the following, what we are going to show is that there is a condensation phenomena, so that the dominant contribution of this amplitude comes from small spin. So it leads to a small spin perturbative expansion. So in the weak coupling limit of this expansion, corresponding to the actually large cutoff limit, the above infinite sum reduced to a finite sum of boundary blocks. So which only depend on boundary degree of freedom, and this sum is finite. Here, infinite ambiguities, because this sum is finite with only finite number of unknown coefficients, and the infinite ambiguities reduce only finitely many boundary coefficients. So this B sigma, and the theory becomes topological invariant and triangulation independent. Okay, so these are the main results. And to show this, let's look at the state sum on a stack of internal phase. Okay, so here, let me first outline the key idea, and then we discuss details in the following slides. The left diagram shows a stack of phases. So each of the phases carries a quantum number k, and which is 2 times the spin. So these phases are identical, and they satisfy bosonic statistics. And actually, this system you will see in the following that is an analog of an ensemble of ideal boson gas. And here, each phase corresponding to a boson particle in this ideal boson gas. Okay. Consequently, there is also an analog of Bose-Einstein condensation of this stack of phases. Namely, in certain regimes, all these stack phases are concentrated at the ground state, K0. So all these spins condensate to the ground, to some ground state spin K0, and this K0 will be called a condensation spin. Okay, so these are basically the picture showing this result. And to be concrete, so let's look at the partition function on this stack of internal phases. Okay, so this is the partition function that shown in the previous slides. And to compute it, we use the inverse Laplace transform to compute this state sum. And this formula is also known as Perron's formula. And this method is actually often used in the computation of loop quantum gravity black hole entropy. This formula basically transforms the state sum to a complex contour integral, and the integrand contains the partition function, this Cs, and which is just a Laplace transform of the original state sum. Okay, and we use this formula, and here are the dictionaries for the quantities. A is the cutoff, and here N labels the states. They are multiplicity and spin configurations. And here alpha N is just alpha pk, the cutoff function. And here beta N is just a product of the phase partition function of identical stacked phases weighted by this parameter lambda. So basically this part and the coupling constant lambda. All right, so here the stack phases are identical because the phase partition function depends on stack phases only through the spin label Ki. Now, because of that, the state sum, this Cc S in the integrand, just reduced to a sum over occupation numbers, just like the grand canonical partition function of boson. And here, this table compares the stack spinfoam phases and a ensemble of bosons. The phase multiplicity act as like particle number, and the spin labels the states, and this Ek, just like the energy level, and this alpha pk is the total energy. The phase partition function times lambda is the partition function of a single boson, or the fugacity. The integral parameter S corresponds to the inverse temperature. So as a result, this partition function Cs can be computed explicitly. It is just the infinite product over state K, and it is very similar to the boson grand canonical partition function. And there's, although there's a -1, just to subtract the ground state, because there's, so we don't have zero multiplicity state in this state sum. Okay, so now the analog with this ensemble of bosons leads to a spinfoam analog of Bose-Einstein condensation. So let's look at this inverse Laplace transform formula of this partition function omega h. So in the integrand, this function Cs is a meromorphic function on the right half plane and has infinite number of poles because there's an infinite product. And the following plot shows so some of the poles in the complex S plane. And so for large cutoff A goes to infinity, the integral is dominated by the residue of the rightmost pole. So these are the rightmost poles and denoted by S star. And these poles has the largest real part, and this is because they are dominating the contribution is because of the exponential factor e to the as in the interval, so this factor pick up poles with largest real part. Okay, so that's why those rightmost poles are making the dominant contribution. Okay, so those dominant poles actually pick up a preferred small spin, which is called the condensation spin. So let's look at a key example that for certain GH, the SL2C holonomies, the absolute value of tau actually reaches the maximum. And so here, this is a plot of the maximum real part of the pole versus the spin k half. So this beta k is just the real part of the pole. So now, so we see that among different spins, the maximum real part of the pole, beta k, occurs as only a specific spin, k0. So this spin where this maximal real part of the pole located at, so it is called condensation spin. So in this case, this condensation spin is just 1/2. So on this condensation spin, the real part of the pole reaches the maximum. So this beta k0 at the condensation is at the condensation spin is the global maximum of the pole's real part on the space of both G and K, and it corresponds to the dominant contribution in the partition function. So result from that, so this is the leading asymptotic behavior of the state sum of the stack of phases, and this leading behavior is just a single phase partition function tau at the condensation spin k0 to a certain power. And the power is the total number of phases, because A here represents the maximal energy, and EK0 is the energy level of the condensation. And so it indicates that the dominant contribution comes from the configurations where all the stack phases are at the ground state k0. So this is the analog of the Bose-Einstein condensation. So when lambda is finite, then the condensation spin is always small. The condensation phenomena occurs at UV regime. And the value of k0 actually relates to the parameter lambda. So when lambda is finite, the condensation spin is small. So when lambda is small, the condensation spin becomes large. And this relation may be an analog of the running of parameters with energy scale. Okay, so this plot here shows that for lambda larger, for example, greater than 0.5, the condensation is always at Lloyd spin 1/2. So when lambda become smaller, spin 1/2 and spin 1 may contribute evenly for a specific value of lambda. In this case, they are both condensation spins. So as lambda become even smaller, the condensation spin become spin 1. So when the condensation spin becomes large, the theory flows away from the UV regime, because as I mentioned in the previous slides, and the analog of the scale in loop quantum gravity are the expectation value of the spins, and so these k0 are basically the expectation value of spins in this case. So here the IR regime so corresponds to large condensation spins, and correspondingly lambda approaching 0. In this case, the stack amplitude just reduced to the usual spinfoam amplitude, which is defined on the root complex. Now we just plug result into the full stack amplitude, and now the amplitude reduced to a path integral form, and with the UV action S. And here the coupling constant is just 1/n, and n is the number of phases at the condensation spin. Similar to QCD, the UV regime corresponding to the weak coupling limit, because the condensation spin in this case is small and the cutoff is large. So this n is a large number. Okay, so by the station phase analysis, we need to look at the solution. Basically, in this weak coupling regime, we can study this path interval by using station phase analysis. So in this station phase analysis, we need to look at these solutions of the equation of motion. So corresponding to the real part of the action equals to 0, and which is the maximum, as well as the derivative action equals to 0. Okay, so these solutions form so-called critical manifold, because each solution are usually called critical point, and the set of solutions are called critical manifold. So these are the results for the solutions. So on the critical manifold, the SL2C holonomies, so SL2C holonomies are reduced to SU2 lattice connection, where SU2 holonomies, HE, plus some on-shell degree of freedom. So those SU2 holonomies, they satisfy so-called S flatness condition, namely they corresponding to flat connection up to plus minus signs on individual phases. Okay? So we have assumed the root complex to be simply connected, and then this implies that up to gauge freedom and all these SU2 edge holonomies are identities up to plus minus sign. So the resulting critical manifold is just a union of disjoint sectors. Each sector is labeled by plus minus signs of the loop holonomy. So each sector is labeled by these plus minus signs for each loop. When we take the recoupling limit, so n goes to infinity, then the integral over the group variables, those SL2C holonomies, the integral localizes onto the critical manifold. And this corresponds to the fixed point theory. Now, let's look at this weak coupling limit. Okay, asymptotically, the stack amplitude becomes a sum of integrals over the critical manifold, because the critical manifold are made by different sectors. And the sum is over these disjoint sectors corresponding to the plus minus sign. So far, we have only worked on the stacked internal phases. The stacked boundary phases corresponding to this omega b, and they are left untouched. And so we just need to restrict them onto the critical manifold by the station phase approximation. And the localization only happens to the integrals that along the internal edge, for the edges EB that connect to the boundary, and their holonomies are not affected, because those holonomies are contributing these boundary partition function. And the integral of all those boundary related contributions, including the holonomies, the integral over holonomies connected to the boundary and the boundary partition function, and put them together, this is called the boundary block. Now let's look closely to these boundary blocks. And so first, let's look at boundary phase partition function. So when we restrict this function onto the critical manifold, the SL2C variables on internal phases, on internal edges, become SU2, because that's the solution of the critical equation, the solution of equation of motion. And then those SU2 holonomies just equals to plus minus 1 on the critical manifold. As a result, this partition function is constant on each sector of internal manifold, and it depends on bulk degree of freedom only through the overall sign, because all those holonomies become plus minus identity. So only those plus minus ones are the leftovers from bulk degree of freedom. Okay, so basically the result is that all those SL2C variables collapse and leave only a single projection operator. And this is the case for the boundary phase with more than one vertices. And this is the illustration of this process. And the lower right is the case that the boundary phase has only a single vertex, and it's from very beginning, it doesn't really involve any internal edges. Okay, so it's already a constant from the beginning. So it's also a constant on the critical manifold. Okay, so there are basically two these cases. Okay, so for the partition function of a stack of boundary phases, so restricted on the critical manifold. So now I define the label sigma. So I define this sigma to be set either 0 or plus minus 1. And so when sigma equals to plus minus 1, so this sigma is just the overall sign of the single phase partition function. So they are basically the plus minus signs left over from the holonomies. And this is the only information left from boundary degree of freedom. And when sigma equals to 0, this is just a label, and this corresponds to the case that the boundary phase has a single vertex. Okay, the boundary block is just a integral over group variables along edges connect to the boundary, and the integrand is just a constant on each sector of the critical manifold, and all its dependent on the bulk information now reduced only to the label, those sigma, because it has those plus minus signs. Okay, so now the key point is that these boundary blocks only depend on the boundary degree of freedom. So firstly, it depends on boundary graph. So these are all the degree of freedom that those boundary blocks depends on. So it depends on the boundary graph of the root complex and the stacked graph generated from the root graph. And this is like, so the first graph is the root graph, and those are the graph generated from the root graph. Second, it depends on those plus minus signs. So the discrete degree of freedom sigma equals to 0 or plus minus 1 for each root boundary link. It depends on the boundary SU2 holonomies and boundary spin cutoff and parameter lambda. And these are all the variables that boundary blocks depend on, and all of them are boundary degree of freedom. And therefore, okay, so moreover, we can freely send the boundary cutoff AB goes to infinity and define the boundary block as a linear functional of spin networks. And these are the formula to make those boundary blocks mathematically well defined and independent of cutoff. And so when cutoff is infinite and the boundary block is the infinite sum over graphs, when integrating against any spin network states on finite graph, and this limit is actually trivial. Okay, so yeah, this is just mathematically defines the boundary blocks as linear functional over spin network. Okay, so now we can put them all together. And the key point is that the boundary block is a constant on each sector of the critical manifold and depend on the sector S only through the label sigma. So the sigma is only left over information about the sector sigma. And so it can be just factored out from the integral. So all other bulk degree of freedom are just decoupled in this integral, and you can just factor this boundary block out and integrate out all the other bulk degree of freedom. And the leading order of the stack amplitude is just a finite linear combination of these boundary blocks. This is finite because the label sigma is finite. Okay, so all dependence on the interior of the complex now entirely reduced to a finite set of coefficients. So B is B sigma, but there are only finite number of them because the label sigma is a finite. It's finite. So as a result, infinitely many degree of freedom in the bulk just decouple, and except for finitely many. Consequently, you can also summing over root complexes, but these summing over root complexes become trivial at the leading order, and the complete amplitude is still a sum over the same set of boundary blocks. And the infinite set of coefficients is just absorbed into a finite set of coefficients because so it's like you only have this finite number of boundary blocks, and no matter how you sum those amplitudes, you still only have finite sum. So and those unknown coefficients basically absorb all the infinitely many unknown ambiguous coefficients. Okay, so in this result, these infinite ambiguities of those coefficients Ck just disappear. And remember that these ambiguities are the triangulation dependence of spinfoam. Now they just disappear. So the theory is independent of triangulation. And the leading order is just the weak coupling limit. And this is the fixed point because the theory is topological and scale independent and triangulation independent. The complete amplitude at the fixed point is a finite linear combination of these boundary blocks. So given the boundary root graph, the boundary blocks spans a finite dimensional vector space, and the fixed point amplitude is just a vector in this vector space. So this is like a typical feature in topological quantum field theory. All right, so all these discussions shows that loop quantum gravity is asymptotically topological, and so this is basically the formula that I showed at the very beginning, so the previous slides show some details how to derive it. Okay, so now suppose we go beyond the leading order of the perturbative expansion, and the perturbations actually introduce defects to the topological theory and make the bulk degrees of freedom propagating. So we have seen in the previous discussion that this perturbative expansion is just the same as summing spinfoam amplitude over lattices, because this expansion is just derived from summing spinfoam amplitude over lattices. The spin cutoff in the full spinfoam theory has to be finite, so because it plays a role relating to the coupling constant in the expansion. Moreover, as I said earlier, this spin cutoff usually relates to the cosmological constant. So this is also consistent because cosmological constant is finite. So when the condensation spin become large, so in this case, this n, the number of stack phases become small because the condensation spin large and this K0 become large. But suppose you take fixed number of the cutoff is fixed, and then this number becomes small, and then this we can't do the large n approximation anymore, and so it means we enter the strong coupling regime, and the UV perturbation theory just fails. So which means in the strong coupling regime we have to use lattice theory, just like in QCD. We have to use lattice spinfoam theory at this intermediate regime, and it also means that also in the infrared fixed point is compared in the sense of this n, this infrared regime is also strong coupling regime. So, but we need to develop a different expansion at infrared to study to discover this IR fixed point. Okay, so finally, this is a short discussion of the.
Sorry, Muxin. So we're roughly 50 minutes in. So if you could wrap up in the next 5 to 10 minutes, that would be great.
Yes, definitely.
Thank you.
So they are only like 2 slides. Okay, so this is just a short introduction of the infrared perturbation theory. So as I mentioned previously, in the infrared regime, the spinfoam stack just reduced to a spinfoam on root complex. So here, let's just focus on arbitrary simplicial complex. Now we can write the spinfoam amplitude using the standard path interval expression. And well, this is something discovered even earlier, that the spinfoam amplitude can be written in terms of path integral formula, but this path integral formula is different from the path integral formula I mentioned earlier. But this pass interval formula, in particular, this action, of course, this action is different from the UV action I defined earlier, but this formula is suitable for the analysis in the large J regime. So the previous UV action is suitable for small J regime, but this formula is for large J regime. And the large J regime is the infrared regime, like I mentioned at the very beginning, and the small J and large J corresponding to UV and IR. Okay, so because the spin here relates to the triangle area on the simplicial complex, okay, so we can make a decomposition of J into two parts. So firstly, the area determined by Regge geometry, and the second term is the non-Regge-like area. Okay, and this decomposition actually distinguish the IR degree of freedom and some degree of freedom just to be integrated out. And the IR degree of freedom are those Regge geometries, and those non-Regge-like areas are the degree of freedom to be integrated out. Okay, so now we consider this decomposition as a change of variable, and we plug in the in this partition function, and then we define a IR effective action by integrating out the spinfoam degrees of freedom and these non-Regge-like area. Okay, so these are the definition for exponential of effective action by integrating out this x corresponding to all the spinfoam variables and p corresponding to non-Regge-like area. And only those Regge degree of freedom are those infrared degree of freedom and entering this low energy effective action. Okay, so the resulting infrared effective action is an action of Regge geometry. And it gives the infrared effective theory of classical discrete geometry. Since the infrared regime is the large J regime, and we can apply the station phase and approximation for this pass interval formula to compute the infrared, to this pass interval formula to compute the infrared effective action. So this computation generally involve so-called complex critical point and numerical analysis. There has been recently a lot of work on that. So here are some new interesting results. Is that suppose we can consider perturbations of flat space-time. So in this regime, some analytic computation can be done, and then we can actually, so these are basically the results for this computation, and we can find this leading order of the effective action. So we can compute perturbatively this interval, and we actually find this effective action is just given by the quadratic Regge action. Okay, the leading term is quadratic Regge action plus corrections at order to gamma, the Babel image parameter, and epsilon square, and this epsilon is the deficit angle, the discrete curvature. And this, so the quadratic Regge action is just a classical action of generativity, discrete generativity, and these terms are some analog of a discrete high curvature correction. Okay, so now finally, if we take small gamma, small Babel image parameter, and the long wavelength limit, so we basically recover the spin 2 graviton, and which is the infrared fixed point theory. Okay, so this is end of my talk. On the left is the main message of this talk. On the right, I list some open directions to be studied in the future, and one of the most important study is the functional renormalization group for background independent loop quantum gravity, because as I mentioned at the beginning, that there is an important feature of background independent quantum gravity, so which are very different from the standard quantum field theory, different from the renormalization group of standard quantum field theory, and therefore, so this is a very important direction to study. Secondly, another open problem is the relation to the physical Hilbert space and physical inner product in loop quantum gravity, because that's some long-term goal of loop quantum gravity is to formulate the Hilbert space of the full theory and including the physical inner product. Okay, and next thing is relates to canonical loop quantum gravity, because this is the whole story is developed for spinfoams. And then in this work, we only consider the bulk continuum limit and the fixed point for as a topological theory in the bulk. And the question is, how about the boundary continuum limit? And so far in this work, and the boundary state is fixed, where the boundary spin at work state is fixed. So boundary is still discrete. So the next thing is to understand the boundary continuum limit or boundary renormalization rule flow. And next thing is matter coupling, and the discussion here only concern the pure gravity spinfoam. So we need to understand the matter coupling, and the fixed point will be the same, but the matter coupling will create different type of defects as the perturbation are away from UV fixed point. Yeah, and some others. Okay, I think that's all I want to say, and thanks for your attention.
All right, thank you very much, Muxin, for the nice talk.
Thank you.